Hello, you have seen how resonance can occur on a fixed string, right? The vibrator sends out a continuous transverse wave. So when the length of the string is equals to multiples of half wavelengths, then you get resonance. You get a standing wave with a large amplitude set up here. Now the sound wave equivalent of this is the pipe. So the speaker here will continuously send out a sound wave into the pipe. The sound wave, when it arrives at the closed end, it reflects. When it arrives at the open end, it reflects. Yeah, surprise, yeah? But you have learned this already. The sound wave reflects at both the closed end and the open end. So you got incident and reflected wave that's supposed to become a standing wave. And then you get reflected again, and then it forms another standing wave, and another standing wave, and another standing wave. So accumulated in this pipe is actually many standing waves with pretty small amplitudes. So they're going to superpose, right? What do you get? Most of the time, they superpose to nothing, because most of the time, all these standing waves are not in phase with one another. However, if the length of the tube is just right, matching the wavelength of the sound wave that's being pumped out by the speaker, then all these mini standing waves will be in phase with one another, and they'll superpose to give you a large amplitude standing wave. We call that resonance. So if you adjust the length of the open pipe by slowly pulling out the extension maybe, then whenever the length of the pipe hits those resonance lengths, then you hear a louder sound, because not only will you be hearing the sound from the speaker, you'll also be hearing the sound made by the pipe. So for the A level, you must be able to work out the resonant lengths and the resonant frequencies. And it's rather easy. Let's start with the open pipe first. So since it's open at both ends, whatever standing wave that's formed must have antinodes at both ends. So what is the simplest standing wave that can be formed with antinodes at both ends? Well, we need to stick one more node at the middle, right? So what does that look like? Like this. Antinode, node, antinode. The dashed line is just to show the complete amplitude envelope. So this is not the only one. What is the next one we can do? So for the first one, we have ana, right? So the next one we can do ana. Antinode, node, antinode, node, antinode. And I think you know what is the next one, right? The next one will be ana, which is going to look like this. So are these the only three? Of course not. There are infinite number of possible resonance modes, starting from ana, and then ana, and then ana, and then ana, and then ana. So for this one, we are looking at half a wavelength being equals to the length of the pipe. Remember, antinode to antinode is half a wavelength. For this one, we have 2 half wavelengths being equals to L. Next one, 3 half wavelengths, then 4 half wavelengths, and 5 half wavelengths. Now, in terms of lambda 1, so lambda 1 is this guy's wavelength, yeah? So in terms of lambda 1, this guy's wavelength will be half lambda 1. And this will be 1/3 lambda 1, 1/4 lambda 1, and 1/5 lambda 1. It's quite obvious, right? Because here, for the same length, we pack 1 ana only. Here we packed in 2 anas. Here we packed in 3 anas. So every ana is getting shorter and shorter, right? What about the frequency? So if this standing wave's frequency is f1, then this one's frequency will be 2f1, 3f1, 4f1, and 5f1. Why is that so? Remember, the speed of the wave is constant for all these resonance modes. V is equals to f lambda, and V is constant for all of them. So if you halve the wavelength, you have to double the frequency in order for the wave speed to still be the same. So just like last time, this is called the first harmonic. It's also called the fundamental frequency. And this is the second harmonic, third harmonic, fourth harmonic, fifth harmonic, and so on. Okay, so that's for the open pipe. Let's talk about the closed pipe now. So the closed pipe has a closed end and an open end, which means whatever standing wave that's formed must have node at this end and antinode at the other end. So what is the simplest standing wave that can be formed with node here and antinode here? Well, this one, right? Node, then antinode. So what's the next one? So here we have a na, right? So just do a na here. So what does na look like? Like this. Node, antinode, node, antinode. Kind of looks like a fish diagram, yeah? So what's the next one? Na, of course. Yeah? Node, antinode, node, antinode, node, antinode. Of course, there are more of them. So you got na here, you got na here, you got na here, you got na here. This one will have 9 nas, yeah? So if the length of the tube is L, what is the wavelength of this standing wave? It's a quarter wavelength. So a quarter wavelength is equals to L, the length of the pipe. Why is it a quarter of a wavelength? Well, it's node, then antinode, right? Node to node will be half a wavelength. So node to antinode is a quarter wave. So what about this one? Here we are packing in 3 quarter wavelengths. So 3 quarter wavelength is equals to L. What about here? Can you see that there are 5 quarters here, then 7 quarters here, then 9/4 here. So if this standing wave wavelength is lambda 1, what is the wavelength of this standing? Can you see that it's lambda 1 divided by 3, followed by lambda 1 divided by 5, and divided by 7, and divided by 9? Because here we pack in one na, right? Here we packed in 3 nas. So each na here must be 1/3 the length of this na here. As for the frequency, if this guy's frequency is f1, then this guy's frequency is 3f1. Remember, v is equal to f lambda, and v is the same for all of them. So if the wavelength is 1/3, the frequency must be 3 times in order for the speed of the wave to be the same for all of them, which means this will be 5f1, 7f1, and 9f1. So as usual, this is called the first harmonic. It's also called the fundamental frequency. Now, what's the next one? The next one is not the second harmonic because it's not 2f1, it's 3f1. So the next one is actually the third harmonic. So the first overtone is the third harmonic, and the second overtone is the fifth harmonic, seventh harmonic, and ninth harmonic, and so on. So we like to say that a closed pipe can only form the odd harmonics. So why are the even harmonics missing? Well, because they cannot be formed, yeah? Because we are talking about a closed pipe here, which requires a note and an antinote here. The second harmonic, if it can be formed, it will have to look like this. Note, antinote, note, which is not possible because a closed pipe must have note and antinote. Okay, so here I have all the standing wave diagrams for the fixed string, for the open pipe, and for the closed pipe. The fixed string and the open pipe are very, very similar. In fact, other than the diagrams, everything else are exactly the same. That's because both of them can form all the harmonics. In fact, if you, instead of drawing the displacement notes and antinotes, if you draw the pressure notes and antinotes, even the standing wave diagrams will look exactly like this one. The closed pipe is slightly different in a sense that only the odd harmonics can be formed. The even harmonics are missing. Okay, that's all. Ta-ta!